Okay, let us continue to study the small oscillation of n particle system that has an equilibrium position at the origin. The equation of motion for the n particle system around about the origin, where the origin is the equilibrium position. For example, the equation, if we substitute q equals 0 to this equation of motion, we'll find the all of the generalized coordinates and no acceleration. If we diagonalize these matrices M and A by substituting the trial solution of e to the minus I omega t multiplied by eigenvector, we were able to find out the orthonormal eigenvectors. Then if we multiply the Hermitian conjugate of the eigenvector to the left-hand side, we were able to pull out the contribution of a specific frequency. For example, if I multiply psi dagger r to the a cube, it collects the normal coordinate eta r multiplied by the omega r squared, which is the characteristic frequency of that normal coordinate. If in reverse, the Hermitian conjugate of this will give the eta dagger, because eta r is a number, it is a complex conjugate. In a similar manner, if we multiply the Hermitian conjugate of the eigencat to mq, we can read off the normal coordinate eta r. The Hermitian conjugate of this will give the complex conjugate of eta r. If we write down the equation of motion in terms of the generalized coordinates q, the potential energy and kinetic energy are written in this form, and the Lagrangian corresponding Lagrangian will be the kinetic energy subtracted by the potential energy. And if we substitute them into here, Lagrangian is obtained. As we already have studied, this complicated structure, mixed structure, will be very clean after diagonalizing the matrix A and M by making use of the eigenvector psi r. All of the equation of motion are completely decoupled into n separate single equations. In this normal, just a single normal coordinate has its own equation of motion, and this single equation can be solved in a very straightforward way. After diagonalization, once we find the characteristic frequency, then the expression will be diagonalized, and each non-vanishing elements represent the eigenvalues for the natural frequency, the characteristic frequencies of each normal mode. We can reorganize this kinetic energy contribution in terms of the normal coordinates. It is just a square piece, and this is a matrix form, and if we expand in terms of the states, this eta s, there will be subscript ss. And the potential energy is written in the form, and the Lagrangian can also be written in a very simple way. The expansion of the generalized coordinates in terms of the time-independent eigenstates has a coefficient that is called normal coordinates. All of the time dependence appears in the normal coordinates only. If we make use of this normalization for the eigenvectors, this is the case for the non-trivial mass matrix that has non-vanishing off-diagonal pieces. The completeness relation for that corresponds to this normalization convention will be in this form or this form. You can freely move this mass M to the left hand or either left or right side of the direct product of psi S and psi dagger S. All right. As we already have stated, Lagrangian can be expressed in terms of normal coordinates, and in a similar manner, we can also express the total mechanical energy of the system in terms of normal coordinates. Let us consider the Lagrangian of the system in terms of the normal modes. This normal mode is a column vector of this form, and because there is identity matrix, the square of this normal time derivative of normal mode will be just sum of square of each normal coordinates. And the potential energy contribution, they are all separated into single normal coordinates and with the characteristic frequency squared, omega k squared. Let us find out the equation of motion in terms of the normal coordinates. It is just like another generalized coordinates and simplest coordinates, just like we use the Cartesian coordinates for very simple calculation. All right. Lagrangian is 1/2 eta dot k squared sum over k minus 1/2 omega k squared eta k squared. The Euler-Lagrange equation for this system for the index eta I, let me replace this one with I. No k, not k, but I. We take the partial derivative of the Lagrangian in terms of with respect to the normal coordinate eta I. Then this one vanishes. Only the potential energy contribution survives. We have 1/2 minus 1/2 omega k squared and derivative of eta k squared. Next piece is minus time derivative of the partial derivative of Lagrangian with respect to the normal coordinate eta I. So this derivative for the kinetic energy appears here. Here we should sum over k's. The chain rule can be applied to find the partial derivative to be 2 times eta k and the partial derivative of eta k with respect to eta I. In the case of kinetic energy, this one appears 1/2 and the chain rule can be used to write this one 2 times eta k dot and the partial derivative with respect to eta dot I for eta dot k. As a result, we obtain vector of 2 cancels to find a negative sign in omega k squared and eta k, and this is Kronecker delta ik. Here we have eta k dot and Kronecker delta ik. So if I sum over k, then what we find is just replace all the k's with I. Replace the indices k with I. So this is eta I dot time derivative omega I squared eta I. As a result, what we find is the equation of motion that can also be transformed directly from the original equation of motion. That is from this. Next, we consider triply coupled oscillator. What we have done until now is just find out the equation of motion and found out the solution for the doubly coupled oscillator. And after we obtain the normal coordinates by making use of the diagonalization of an Hermitian matrix, we have constructed until now for treating the small oscillation problem for the n-body system that has a stable equilibrium at some point. So we would like to extend this method to the triply coupled oscillator. To simplify our analysis, we use all identical beads that are connected with the identical springs, where the spring constant is k and mass of the particle is m. Then the kinetic energy of the system is, because it is composed of the three bodies, we just simply compute the 1/2 m times velocity squared for each mass. Here in the figure, we are still considering the case there is no transverse motion and the motion of the massive particle attached to the springs is only along the x-axis, that is longitudinal direction. Next, we consider the spring, the potential energy of the spring. For simplicity, just we consider the change in the string's length in comparison with the state in the equilibrium position. So the first one is attached to the first spring on the left-hand side. One side is attached to the wall, it is fixed, and the change of the length is governed by the length of the displacement of x1 only. That is 1/2 kx1 squared. And the potential energy of the second spring between 1 and 2 should be computed by making the difference between the two coordinates squared. In a similar manner, the potential energy of the spring between the particle 2 and 3 will be 1/2 k x2 minus x3 squared. The third one part, the one side is attached to the wall. So again, just like the case of the first mass, we have x3 squared. We can rewrite this kinetic energy in a matrix form, because this x1 squared, there is no mixed states such as x1 dot, x2 dot, something like that. We have diagonal elements with mass m, and kinetic energy is computed as 1/2 this row vector multiplied by column vector sandwiching the mass matrix. Then that mass matrix is very simple. It's proportional to the unity, the identity matrix, multiplied by the mass of each particle. In summary, we have identical particles of mass m with an identical spring attached between any two particles and the walls. The kinetic energy was a simple sum, and mass matrix was obtained in a very simple way. And the potential energy was the sum of these four pieces that contains the distortion from the original length. If we expand all these squared pieces, we have 2k1 x1 squared and 2x2 squared and 2x3 squared. Therefore, we have 1/2 2kx1 squared, 2kx2 squared, and 2kx3 squared. In addition, there are cross terms. This one appears only for the nearest to neighbor. That means 1 and 2 difference squared generates a minus k x1, x2. 2 and 3 generates minus x1, x2, x3. As a result, we find that the mass matrix can be read off from this expression. For example, 1/2 2k x1, x2 can be written into 2k x1, x2 is k x1, x2 plus k x2, x1. 2x2, x3 can be understood as 2x2, 3, kx2, x3 plus kx3, x2. That means if I multiply this row vector consisting of x1, x2, x3, and column vector x1, x2, x3, the matrix in the middle will have the coefficient k, and then each square has a factor of 2. Each square, 1 square, 2 square, and 3 square has a factor of 2. And this 2 times x1, x2 should be distributed in even form. We don't have to, but symmetric matrix is very simple, and what we want to use is to consider the orthogonality, and that is guaranteed as long as the mass matrix and the potential energy tensor are real and symmetric. Thus, we make this matrix in a symmetric form that can be made by dividing in two equal pieces. So 1, 2, 2, 1, 3, 1, 1, 3, 2, 3, 1, 1, 3. Okay? And 3, 2, 2, 3. Therefore, we have determined the potential energy tensor and mass matrix for this triply coupled oscillator. Just like what we have done until now, the mass matrix and potential energy tensor are real and symmetric. Therefore, it is straightforward to obtain the orthogonal eigenvectors by solving the eigenvalue problem. The solution of the eigenvalue problem can be found in this way. We first define omega 0 squared for simplicity. That is the natural frequency for the single mass and that single spring. Omega squared is now defined by the potential energy matrix divided by mass m, because the mass matrix is just m times identity. Now we introduce the eigenvalue problem. Omega square psi equal omega square psi. This small omega, lowercase omega, represents the eigenvalue. And if we scale out this natural frequency squared for the single mass and single spring case, what we find will be omega 0 squared times lambda, where lambda is a scaleless number. We define alpha to be 2 minus lambda and minus 1 to be beta. Then the determinant of the Scalar equation, the eigenvalue equation, can be solved only if the Scalar equation is satisfied. And determinant can be expanded in two pieces, alpha times this 2 by 2 matrix determinant minus beta times this 2 by 2 matrix, this 2 by 2 matrix that is written here. And expansion will give alpha squared minus beta and beta alpha. We have a common factor, alpha, factorized. To find out the solution is alpha squared minus 2 beta squared. The solution to this problem is alpha equals 0. That means if alpha equals 0, lambda equals 2. And two other solutions are alpha equals plus minus square root of 2 beta, because beta is minus 1. First, let us consider the case of alpha equals 0. If I substitute alpha equals 0 and multiply the appropriate eigenvector with the undetermined elements, we find that the two elements must be the same and with opposite sign, and the one in the middle must vanish. Therefore, simplest choice is minus 1, 0, 1. And normalization of the state can be corrected in this form. Sure, we don't have to put negative sign on in here. Instead, we can also introduce the eigenvector with the 1, 0, minus 1. That's fine. Therefore, this lambda equals 2 case, that means the characteristic frequency is the omega 0 multiplied by square root of 2. Has the eigenvector this. Second, we consider the case alpha equals square root of 2 beta. If alpha equals square root of 2 beta, then if we substitute this value in here, we have square root of 2 in the diagonal pieces, and these two elements are 1. Simple calculation can be made. If I multiply 1, 1, and square root of 2 with an opposite sign, then it is orthogonal to this matrix, is the row vector. So, simplest answer will be this. And if I square this, we find 4. The square root of 4 is 1/2. Multiplying 1/2, we have normalized eigenvector. And the third one has a minus square root of 2 beta that has different sign on this side. That should be equally, these magnitudes are the same, except that the sign is opposite. So we have obtained the all three unit normally orthonormal eigenvectors and those corresponding eigenvalues here and here. So once we find out those eigenvectors, we can construct a matrix that diagonalize the mass matrix and potential energy tensor. Now we have obtained these eigenvectors. And if I combine all three pieces into here, the Hermitian conjugate can be combined to construct a transformation matrix lambda, and lambda dagger can be obtained by taking the Hermitian conjugate of this. So Let us bring this column vector, exchanging this row into column into row, and put this the first row. Hermitian conjugate, because they are all real, Hermitian conjugate is just the transpose. The second row can be obtained from here, and third row can be obtained from the third one. Okay, and the Hermitian conjugate will be the transpose of this matrix, and lambda dagger is obtained as. Because the normal modes can be obtained by multiplying the matrix lambda to the generalized coordinates, we have three coordinates, so just multiply this transformation matrix lambda to the column vector consisting of x1, x2, and x3. The final result will be like that. Once you find out alright, and then we know that the equation of motion for each normal coordinates is trivial. The solution will be just a linear combination of sine and cosine with the characteristic frequency given specific case. For example, omega 1, omega 2, and omega 3 are given in this form. Once you have solved all those problems, you need to return to the original coordinate. Original generalized coordinate Q can be obtained by multiplying lambda dagger to the normal modes. Just like what we have done in the previous case, this three-body problem has the same structure. The structure that we have already determined, constructed, is general for any arbitrary number of particles. Let us extend our method to consider a vibrating string, especially by a loaded string. I mean, in the next chapter, we take the continuum limit to consider the vibration of a continuous string, uniform string. But before we consider that problem, we consider massive particles. For example, for the simplest case, two massive particles loaded on a string of tension tau. The spacing of two adjacent beads are all equal, and the magnitude is spacing is d, and we have identical mass small m. Then the kinetic energy of all of these two particles are like this. Here we consider only the transverse motion. I mean, the direction, longitudinal direction, is the direction of the string without the oscillation, and transverse longitudinal motion is just like the spring problem we have considered until now. All right, and we consider the transverse motion, and there are two transverse directions. If we consider is x as the horizontal axis to be the x-axis, we have two more axes, two transverse axes, y and z axis. However, in order to simplify our problem, we just consider the transverse direction is there is only a single transverse direction. In that case, the kinetic energy of the two particles is just a single, expressed in terms of single coordinate for each particle. As usual, But just like what we have done already, Lagrangian of the system can be expressed in such a way. And we'd like to find out the transformation matrix lambda consisting of eigenvectors. And at the end of the day, we'll express this system in terms of normal coordinates. Remember, the identifier k equals 0 and k equals 3, that is n plus 1. And k equals 1, k equals 2, and so on. So k equals 0 is the initial particle's position, but that is fixed on the wall, and there is no displacement at all. So Q0, we can introduce Q0, but Q0 is exactly 0 for any t. In addition, we have Q n plus 1 is exactly 0 for any t. This is true for any number of beads. Now, by making use of the kinetic energy, again, we find the mass matrix is trivial. The mass matrix is of the form m times unit matrix. Wait a second. So let us consider the equation of motion. Equation of motion can be constructed from this figure. The motion of this bead is only along the transverse direction. The string is attached to this mass. The force is the tension, and tension has a longitudinal component and the transverse component. There are two forces. If the angle is small enough, the tension is almost the same as the longitudinal force. And the two forces are opposite, equal and opposite, and we do not allow the motion along the longitudinal direction. Therefore, the longitudinal force exactly cancels. The only force along the transverse direction is this, and that can be obtained by multiplying the tension multiplied by sine theta. And direction is upward in case this is the ith bead, and this is I plus 1th bead, and this is I minus 1th bead. If we order this one to be increasing, this form, then the transverse force applied to this ith particle due to this I plus 1 is via this tension, and tau times sine theta I plus 1. The left hand side will be the angle theta I, and that can be computed with tau sine theta I. Here, this is a positive, so we put the positive sign on it, and this is downward, so we put negative sign on it. The sine of this angle can be computed by the difference of the height, qi plus 1 minus qi, and we can rewrite this, to flip this sign and order this one qi minus qi plus 1. The second one has the force minus tau sine theta I, and sine theta I can be computed with qi subtracted by qi minus 1 divided by the equal spacing d. Sure, this d is the horizontal spacing, but this distance is almost same as this distance up to a correction of a quadratic piece. All right. So the equation of motion for the ith bead will be mass times acceleration of the transverse coordinate. Will be the sum of these two. The two contributions can be added to find out tau over d, and there are two qi's with negative sign, and a single qi plus 1, a single qi minus 1. Okay, we are ready to compute the potential energy. The potential energy of this particle can be computed by integrating this force multiplied by negative sign on it with respect to qi. However, the system has the single potential energy that is unique, so that can also be computed by making use of the integral with respect to qi plus 1. Therefore, this one can be done in a repeated way. First, we find the integral of this one. This q1 integral brings in q1 squared. The qi integral brings in 1/2 qi squared. So this one 2qi became minus 2qi became minus qi squared. And these two pieces are independent of qi. So what we want to do is just to multiply qi. In a similar manner, we can carry out the calculation for the qi plus 1, and this one will give qi plus 1 squared piece and mixture. This mixture is the integral of this one. For example, this can be done by replacing I with I plus 1. By replacing I with I plus 1. So the I minus 1 became I became I plus 1, and qi becomes a qi plus 1 squared, and this one qi plus 2 and qi plus 1, something like that. So if I combine everything all together, we should not add these two pieces, but we should match the conditions, boundary conditions for the adjacent variables. We must not add them up, but the potential energy is a function of q1 to qn. So if I combine everything together, we find that there are squared pieces and product of adjacent coordinates. Okay. For example, just like what we have done in the case of the spring, longitudinal motion of the masses attached to identical springs, the resultant potential energy is of this kind of form. There are two QIs and equal magnitude but opposite sign for Q1, Q2, and so on. If there are many more particles, this structure is continued to the end. Here, the last one is attached to the wall. The right side last one attached to the wall. So the structure is very similar to the case of a spring. That means it is just a difference difference of adjacent b's, the transverse coordinates difference squared. But the reason why we have just a single square is the adjacent coordinate is just war, and war q0 and qn plus 1 are all vanishing. So this q2 is supposed to be q2 minus q3, something like that. And the q1 is q1 minus q0, something like that. The reason why we have vector 2 is in order to complete the square, we multiply the number of 2's in the numerator and divide it by the denominator. Alright, so now we have the kinetic energy, that is 1/2 q1 dot squared, q2 dot squared. We would like to replace this one in the matrix form. Then it becomes qi dot qj dot delta ij, because this is for 1, 1 and 2, 2 pieces. There's no contribution for q1 dot q2. This mixed term does not appear in this case. Potential energy was found to be tau over 2d multiplied by the sum of this square of the difference of the transverse displacement for adjacent b's. If I expand everything altogether, what we find is this one. We vector this original vector, keep as it is, and we rewrite this one as a product of a coordinate, generalized coordinates, column vector and row vector, and the potential energy tensor. We know that q1 squared and q2 squared has a factor of 2. That means diagonal elements are a factor of 2. This one is multiplied to the product of q1 and q1. Because we have minus 2 q1, q2, that can be equally distributed into q1, q2, and q2, q1. Because the expansion of this product, we find q1 is multiplied to here and there. So this minus 1 stands for the coefficient of q1 and q2 product. This minus 1 represents the coefficient for the product of q2 and q1. Therefore, now we can construct we can rewrite this potential energy as 1/2 q dagger aq, where the potential energy tensor A is tau over d and this matrix. Because mass m is factored out, Lagrangian can be constructed by factoring this 1/2 m out. We have q dot dagger q dot minus q dagger omega square q, where omega square is this potential energy tensor divided by m. Now we are ready to solve this problem by rewrite this problem in terms of the normal coordinates. Eigenvalue equation can be constructed in this way. We pull out the over factor tau over omega d, tau over md, scaling factor out, and the scaleless eigenvalue is chosen to be lambda. The solution for this will give the two eigenvectors. The two eigenvectors can be combined to find out the transformation matrix lambda, and its Hermitian conjugate lambda dagger. The lambda is a unitary matrix. By making use of these transformation matrices, we can diagonalize omega squared to find that the frequency is tau of MD 1 and 3 respectively. Now we are ready to attack the problem with n beads on a string. Again, the equation of motion has the same structure. The ith particle has the force coming from the I plus 1th particle and I minus 1th particle. And equation of motion has the identical form as what we have done for the two particles, two equal beads on a loaded string. And the potential energy can be computed, written in the same manner. What we have done is just change the upper limit from n3 to n. This n-bead problem of equal spacing d, the equation of motion is still the same. Let us repeat the calculation for the potential energy. The potential energy can be computed by integrating the minus external force over for each coordinate. And this can be obtained by integrating over qi and integrating over qi plus 1 and integrating over any. And those relations can be obtained for the various cases. In order to satisfy all these conditions altogether, what we really find is q squared, everything q squared from the beginning to the end, and everything with the minus product of two coordinates that are adjacent. So 1, 2, 2, 3, and so on. In a similar manner as we have done in the previous way, we multiply 2 in the numerator and divide by 2. Then we can complete the square for all the pieces in the middle. That is to reproduce this result. The extension of that method will allow us to find out the potential energy tensor. All the diagonal pieces are all 2, and among all of diagonal pieces, everything is vanishing except that the two adjacent pieces have interaction with minus 1s. Okay, let us check this one if it is true. We have already obtained the expression for the potential energy, and by definition, the potential energy tensor Aij element of the potential energy tensor can be computed by taking the double partial derivative with respect to the two coordinates qi and qj, and substitute the equilibrium position q equals 0. Then what we find is the overall coefficient the tau over 2d and second order derivative and this sum of squares. Qi differentiation is to be made first. Then by applying the chain rule, we have factor of 2 and this factor in here. And then we take the partial derivative with respect to qi. The result is like that. And this one gives the canonical delta. Delta ik minus 1. All right, and then the next derivative is to be made. Then this differentiation is applied to this one because the remaining piece is just a constant. Then this factor of 2 cancels, and we still have another canonical deltas. This is delta jk, this is delta jk minus 1. We expand these product, the delta jk, delta ik. So we rewrite this one as delta ik and delta jk. And delta, this delta jk, these two, jk minus 1, ik minus 1, and this one. And in the middle, we have negative sign, jk, and ik minus 1. Ik and jk minus 1. Okay, let us first consider these two pieces first. These two, ik, jk, and ik minus 1, jk minus 1. We know that k runs from 1 to n, and k equals 0 and k equals n plus 1 is not to be considered because they are just fixed coordinates to be 0. So in the summation, we consider the indices in the range from 1 to n only. In that case, this k in the first term begins with the 1 and ends up with n plus 1, but we ignore n plus 1 that does not contribute at all. Thus, our final result is from 1 to n. Next one, this one begins with 0 to n, but 0 does not contribute at all. Therefore, these two sums are equal. So 2 times from k runs from 1 to n, delta ik, delta jk. That means this contribution is 2 for diagonal elements. That means all of the diagonal elements were 1, 1, 2, 2, k equals 1, k equals 2, k equals 3, 2k equals n. All the diagonal elements are 2, right? And then we have these two pieces. These two pieces can be written in the form. Just copy it from k runs from 1 to n plus 1, blah, blah. Now, let us consider this one. K runs from 1 to n plus 1. That means k equals 1 means k minus 1 is 0. That does not contribute at all. So from k equals 2, it becomes 1 and 2. So 1, 2, 2, 3, and so on. And at the end, the last term is n plus 1, but if it becomes n plus 1, it does not contribute. So what we want to do is consider k runs from 2 to n. If k runs to 2 to n, then we can shift the k by k runs to 1 to n and add k plus 1. So it becomes, this one becomes ik, this one becomes jk plus 1. In a similar manner, we can add these two with k by k plus 1, then final result is that, like that. This means I and j are differ by 1, and j is greater than I by 1, ij. That is this. All these lists with negative sign is represented by this one. And all of these is represented by this one, because I is greater than j. J is missing. I is greater than j by 1. Then this is all minus 1. So we have reproduced this potential energy tensor exactly. Now we are ready to solve the equation of motion, and we introduce a trial solution in a step by making use of separation of variables. Separation of variables shows that we have vector of time-dependent vector and space-dependent vector. So kth bit has index k, but if you ask why we are introducing this, I don't care. Just try the separation of variable. If it works, that's fine. So we introduce this trial solution. If I take the double time derivative of this trial solution, we always find out minus omega squared. Substituting this trial solution into the equation of motion, what I find is a minus omega squared for double time derivative and these exponential factors. And remaining three pieces has the same time dependence, so it is not to be altered. Only the k dependence appears in the qk minus 1, qk, and qk plus 1. If we factor out e to the ikr and e to the I omega t, absolutely divide, then it becomes minus omega squared. And tau of md, and the change is replace just the k with 0. Then we have e to the minus I gamma minus 2 e to the I gamma. This sum is to be replaced with the 2 times cosine gamma. And as we know, this 1 minus cosine something is 2 times the sine square half of that angle. As a result, the characteristic frequency is found to be like that. The fact that we have found characteristic frequency that satisfies this equation means we have indeed solved this equation by this trial solution. The trial solution worked fine. Then, finally, we can write down the answer. E to the minus I omega t means it is either e to the I omega t or e to the minus I omega t. So the time-dependent factor is a linear combination of these two pieces. And spatial contribution is a linear combination of e to the ikr and e to the minus ikr. And the frequency in here is completely determined in this way. However, we can further simplify these expressions by making use of the boundary conditions. We know that the left hand and right hand of the string is fixed. Therefore, Q0 and Qn plus 1 is exactly 0. Thus, the expansion in terms of cosine and sine is very useful. So, as far as this spatial vector is concerned, when we substitute k equals 0, it must vanish. If substitute k equals 0, this one vanishes, but this one survives. That means A prime is vanishing. Therefore, we have a sign contribution only, but we have an additional contribution constraint, Qn plus 1 equals 0. If we substitute k equals n plus 1, then sine n plus 1 gamma must vanish. That means that is n pi, where n is r pi, and r runs from 1 to n. The reason why we take these n values is that it determines the characteristic frequency. As we know, the n by n Hermitian matrix is diagonalized, and its eigenvalues are at most n. And number of eigenvalues for the characteristic frequency should be n. Therefore, we have indeed found every frequency to be exactly the same as this number, where r is replaced with from 1 to n. Note that r equals 0 and r equals n plus 1 gives exactly 0 for this answer. That means this answer becomes trivial solution. and we are not interested in the trivial solution. That does not make any sense for the vibration. It does not vibrate at all. Now, we are ready to find out the eigenvector. Eigenvector is now found to be sine something pi over n plus 1, where something runs from r, 2r, 3r, 4r until the end. That value is nr. I'd like to find out the normalization in order to find out the completeness relation that is quite useful to project out the normal frequency. We need to square this and find out the magnitude of this eigenvector. First of all, because M and A are both Hermitian, we expect that as long as the indices are different, they must be 0. I don't have to prove the very complicated calculation. It is already proved. Next, we consider the R equals S case. Then, this is the answer is this. Let us prove immediately after this page. If I make use of this normalization, then what I find is the inverse of this square root is to be multiplied to the original eigenvector to find out the normalized eigenvector. Right? Does the vanishing scalar product for distinct eigenvalues can be expressed in such a way. This is all of the signs, and with the single r, and another identifier. This is r and s, and common value for k runs from k equals 1, k equals 2, and so on, and summed over k from 1 to n. That is a vanishing. It is because these are the eigenvectors for the Hermitian matrices. In order to find out the normalization for the eigenvector for the Lodid string, we first consider the sum of the geometric sum of these cosines. Cosine multiple of A, where multiple runs from k equals 0 to n. This cosine can always be expressed in terms of the real part of exponential IKA. And now it becomes a geometric series. This geometric series can be solved, can be summed as it is. S runs from k equals 0, it's a 1, begin with 1 and end up with n, so e to the I n a. If I multiply this common factor is multiplied to find out that this is shifted and this is shifted. And everything in here, in between, they are the same. So if I subtract, then s is factored, and we have 1 minus e to the ia. And everything in the middle cancel, and only these two pieces survive. So 1 minus e to the I and plus 1a. Let us divide this one, both sides, divide both sides by this one, and we have s equals this divided by this. We can reverse the order. This minus sign appears twice, so we have the same number. We factor the half of this phase out, then the remaining piece has e to the I theta minus e to the minus I theta style. Okay? And this over vector has a phase of half of this original one. And in the denominator too, this one cancels the over vector in the denominator to find the exponential I, half of n multiplied by a. And these two are, if we divide this by 2i and 2i, then we find this is a sine, and this is sine 2. So this is, numerator is a sine n plus 1, 1/2 of n plus 1a, and this half of a. Now, substitute this result in here, and take the real part. As we know, this value is a real number, and this is complex number. The real part can be obtained by taking the cosine part of this exponential. So this is cosine 1/2 na, and this vector is copied. This is for the summation of cosine Ka from k equals 0 to infinity. We have cosine alpha minus beta is cos sine sine. Cosine alpha plus beta is like that. The difference of these two will find the product of sine and sine. So sine alpha times sine beta is 1/2 cosine alpha minus beta minus cosine alpha plus beta. The summation k runs from 0 to n for the sine k alpha and sine kb, ka, kn, kb can be made by applying, by making use of this expression. In here, the left-hand side and right-hand side can be added up by making use of the formula just we have derived. If we substitute this formula, we find the summation of a sine ka, sine kb from 0 to n is like that. In the special case, what we want to calculate is the special case for a equals b. When a equals b, we can compute this one with by making use of the L'Hopital's theorem. In the limit a goes to b, the argument of the two signs becomes infinitesimal. Therefore, we take the derivative of the argument of both sides, and we find that it is a n plus 1. Therefore, this sum sine ka squared, so when a equals b, sine ka squared summation summed over k from 0 to n is 1/2 n plus 1, and cosine na and sine n plus 1a, sine n plus 1a over sine a. What we are interested in is a special value for the case a equals r pi over n plus 1. If I substitute this result in here, the second piece that has a sine factor, this cosine na, sine n plus 1a divided by sine a, has a factor of sine r pi. Sine r pi right? So this one is completely vanishing because it is not mismatching. It is non-vanishing because of n plus 1 in the denominator. So if it is completely, because it is completely vanishing, the sum over sines, if you substitute k equals 0, it does not contribute at all. So it is the same as summation over k from 0 to n is the same as summation over it is summation over is the same as k runs from 0 to n in this case. So we have proved that this value is 1/2 of n plus 1. Therefore, this representation for the eigenvectors is completely proved. All right. Now, we have found that the eigenvectors for the natural frequency with omega r equals 2 times square root of tau of md sine 2 m plus 1 r pi is this, and this expression is exact. So we can make use of this to find out the diagonalizing matrix, transformation matrix for many cases. This is for n equals 2 and n equals 3 and n equals 4 and even n equals 5. As we can see, these matrices are symmetric, and even the Hermitian lambda dagger is lambda, Hermitian and unitary. Lambda dagger is because lambda dagger is inverse. The matrix itself is the inverse. In the previous case, we put the negative sign on it. However, this expression gives a negative sign in the diagonal piece. So that's the reason why this lambda has a different sign. But you remember, the determinant is not plus 1 in this case because it contains an inversion. But our previous derivation did not consider the inversion, so lambda inverse and lambda inverse is a lambda dagger unitary. However, lambda was different from lambda dagger. Anyway, each column or each row represent the eigenvectors, the explicit form in numerical value for this analytic expression is represented here. And 3x3 case and 4x4 where A is this and B is this, and even 5, and it is using automatic calculator. We can make use of computer to find out this vector, and by making use of this vector we can construct the unitary matrix that diagonalizes the Lagrangian, the mass matrix, and potential energy tensor as well. Now we have completed in solving the equation of motion for n beads on a loaded string with the tension tau and with the identical mass of m and with equal spacing d. The frequency of each normal mode has this kind of form. In the limit n goes to infinity, you will find that this r begins with a very small number, but it ends up with the value of sine half a pi. Then it approaches 1 as n goes to infinity. Anyway, the number of distinct states, distinct normal modes, is the number of beats exactly, and number of frequency allowed is exactly n. That is quite important. And the normal mode can be found by finding out the normalized eigenvectors that are completely determined. The multiplication of Hermitian conjugate this eigenvector to the generalized coordinate vector, then you can select a single normal coordinate. And these expressions can be useful. And again, with the same formulation, the generalized coordinate representation can be compactly expressed in terms of normal mode expressions. That's it.